A very good afternoon to all. It is a great pleasure and honor to be here with the august audience. My sincere thanks to the organizers for this opportunity. The topic of my today talk is Aero-Engine development for indigenous programs. The outline of my presentation will be the current indigenous Aero-Engine gas turbine engine development with current infrastructure and ecosystem, future Aero-Engine programs for indigenous platforms, then development of a advanced high thrust class engine like for AMCA, and what is my way forward for these things. Before going to the current indigenous Aero-Engine development, I want to bring it out here. The fighter aircrafts or the trainers or from the helicopter or for the transfer aircrafts, the engines are, most of the things are either licensed manufacturing, for example, AL31FP for Su-30, or we are importing the engine along with the platform like Mi-8 for the Rafale, or we are importing the engine for the indigenous platform like GE40 for IN-20 for the LCA. However, we are having a sustained indigenous Aero-Engine development, just what I will be bringing out. In the indigenous development of the Aero-Engines, in the turbofan vertical, we are going ahead with the GTRE, the Kaveri derivative engine for the remotely piloted strike aircraft. Then HL is going ahead with Hindustan turbofan 25 kilonewton for the trainer. Then small turbofan engine, GTRE is developed for the submarine launched cruise missile and long range land and cruise missile. Coming to the turbo shaft vertical, HL is doing for the Hindustan turbo shaft engine, which is 1200 kilowatt. I will be bringing out what is the status. Coming to the Hindustan turbo fan engine, that is 25 kilonewton engine, HL already has carried out the core engine testing. Now the full engine testing on the test bed, they're already there going ahead with that thing. Similarly, for the turbo shaft engine, the 1200 kilowatt also, they completed the gas generator testing. Then they're going with the free power turbine with the gearbox. Already ground test trials are going on. And for 260 kg engine, the 2.7 kilonewton engine, NAL, they completed the detailed design and they are the module level testing, they are going ahead. Now, the Indian industry is at the lot of people like startups, MSMEs, they started the developing of some of the things like Turbotech, Bharat Forge Limited, UMS, Paninian, Raghuvamshi. Very recently, DG Propulsion, they completed a testing of 100 kg. So a lot of R&D as of now, it is going even in Indian industry. Coming to GTRE, I will take 2 minutes here. Coming to the Kaveri engine, we have built 13 engines and we have carried out 3004 hours of testing, which includes the GTRE test bed, 180 hours of altitude testing at Central Institute of Aviation Motors, Siam, Russia, 57 hours of FTB testing on IL-76. After we can see the Kaveri engine on GTRE test bed with the full afterburner mode, that is the reheat mode. The rightmost side, the Kaveri engine in the altitude test bed, where we simulate the inlet total pressure, inlet total temperature, corresponding to the altitude and the forward Mach number and the exit static pressure corresponding to the altitude. There we have evaluated the engine performance and for the full flight envelope, and we could achieve 49 kilonewton as against 52 kilonewton. There is a 5% shortfall in the thrust in the dry mode. Whereas in the afterburner mode or reheat mode, we could achieve only 71 kilonewton as against 81 kilonewton. There is a 13% shortfall and the engine weight is 200 kgs is more. Then we could able to complete all the component safety life related tests like overspeed, burst margin, cyclic spin, all the things. But the non-availability of certified Kaveri engine as per the LCA program could not give, that's why it is delinked from the LCA. However, we have gone ahead the Kaveri derivative engine, right now what we are working with for the remotely piloted strike aircraft. In fact, RPSA being developed with the achieved thrust of Kaveri engine in the dry mode, that is 49 kilonewton, and the envelope and the achieved weight, they were doing the RPSA itself. Now, the Kaveri derivative engine had a 75% commonality with the Kaveri engine and RPSA specific. For example, because it is a stealth aircraft, it is a serpentine aircraft, so serpentine intake, the distortion levels will be very high, and earlier we were having a fan flutter, both the things with a new fan, that is high distortion with flutter free, we are designed and developed. Similarly, this is a remotely piloted, so autonomous, full authority, digital control, we are designed and developed. And it is a strategic platform, that's why we have gone ahead with design and development of fuel control system with enhanced redundancy with the cross-channel data link, and we designed and developed integrated to the Kaveri derivative engine, and we have tested in GTRE and 75 hours of altitude testing at Siam, Russia. There we have demonstrated the performance and operability with unrestricted carefree throttle movement, where we had a severe issues in Kaveri engine because low speed stalls, fan flutter, LPT blade resonance issues. Everywhere we could able to go to software changes, actually it will be called jump. But in Kaveri derivative engine, with these design mods, we could able to address all the issues, and with which is required unrestricted carefree throttle movement, we could able to do. Very recently, we have completed 50 azimuth cycles, which gives the confidence from the structural integrity point of view, and we integrated the aircraft accessory gearbox, that is AMAC-B, with PTO shaft, with JFS, and aircraft hydraulic pumps, integrated IDG, and the with all aircraft, whatever is there simulated, we have done, and we have gone ahead with 1.5 hour, the whatever the mission we have simulated by the RPSA, and we could able to complete. And coming to the small engine side, last year we could able to successfully flight tested our small turbofan engine, which is a 4.5 kilonewton, meeting all the mission requirements, that is C-skimming and the terminal pop-up at the end of that thing. With this, we had no how, no why for the fourth generation, say 75 kilonewton, but with a thrust to weight ratio of 6.5, because our thrust is 71 kilonewton and almost like 1250 kgs, what's supposed to be 1050 kgs is the weight. With this, we could able to design validated tools up to 6.5 thrust to ratio. We had the capability in GTRE and Indian industry. Then we infrastructure for the aerodynamic testing like compressor, combustor, turbine, afterburner, then like a overspeed burst margin, cyclic spin, all up to 75 kilonewton thrust engine, we have the things, and manufacturing facilities also we are having. For the component manufacturing of Kaveri derivative engine, small turbofan engine, even we have gone ahead with a turbocharger with the Indian industry partners. Across the India, we can see all the people we have gone ahead. And most of them today, they are the part of the global supply chain of the OEMs. Now we are going ahead with our Kaveri derivative engine under development cum production partner DCPP with the Godrej, and the small engine, small turbofan engine, we are going with the BrahMos Aerospace BATL Thiruvananthapuram, and we have gone ahead with our turbocharger with Turbo Energy Limited, Chennai. Then we are closely interacting with academia, is one of the things everybody is talking. We have 15, DRDO had the DRDO Industry Academia Center of Excellences. For COPT we call Center of Excellence for Propulsion Technology, Gas Turbine Materials GTMAP, then Air&B Propulsion. With TDF, we are working with all Indian academia and we are developing what all the technologies I will be coming later. Now coming to the future Aero-Engine programs for the indigenous platforms, everybody talked about. Now LCM Mark II, 98 kilonewton engine is the requirement, that is 414 INS6. We are going ahead, India will be going ahead with the, planning to go ahead with the MTOT for the 414 INS6. Coming to 110 kilonewton, which is for the AMCA, of course is for IRA conditions, the thrust, which meets the full mission requirements. We are going ahead with the first 2 squadrons with the 98 kilonewton and remaining 5 squadrons will be with the 110 kilonewton for the AMCA. That I will be coming co-design, co-development for that engine. Then IMRH has brought it out, the JV with Safran and HL Aravali. Then we are planning for our own indigenous HALE, for which almost like a 1200 HP turbo prop engine is required, and other small turbofan engine, small turbojet engine for the expendable engines for our cruise missile applications. Now before going to the advanced high thrust loss engine, generally 5th generation engine is characterized by thrust to weight ratio of 10 and a turbine engine temperature of 2000 Kelvin. So this is for the 5th generation engine, where the fan pressure ratio of 5, overall pressure ratio of 30, a bypass ratio of around 0.5 with single crystal turbine blades with the electron beam physical vapor deposited TBC thermal barrier coatings, and with the integrated engine and flight control systems. Coming to the 6th generation, the thrust to weight ratio will be in the order of 14, whereas the turbine entry temperature will be 2200 Kelvin, which is almost near to the hydrocarbon flame, adiabatic flame temperature maximum itself 2300 Kelvin. So GTRE or DRDO proposes to co-design, co-develop the 110 kilonewton with know-how, know-why, so that tomorrow any variants or any new engine, by acquiring the technology blocks, design as well as manufacturing, India we can do on our own. So as I said, thrust to weight ratio of 10 with a hardened part life of 2000 hours, low specific fuel consumption, lower size, modularity, then coming to reduced signatures, the technology levels are advanced actually in terms of design and analysis, materials, manufacturing and processes. That's why we propose the engine house, international engine house should lead in the design and development of the core engine, that what we call HP compressor, combustion and turbine, whereas DRDO will lead fan, LP turbine, then afterburner and the subsystems like fuel system, lube system, gearbox, etc. So with this, we want to propose, we proposed the development model. Here the design, development, flight testing, the main stakeholders are DRDO, that is GTRE, and the International Engine House. The other stakeholders, major stakeholders are the Indian industry partners, where we want to go to develop, manufacture, it is required 15 engines for the testing and 10 years for the 10 engines. Totally we require 25 for the flying and qualifying. So we should go through the DCPP for the manufacturing. He is one of the major stakeholder. Similarly, Semilac and DGQA for the certification and qualification. Then IF for the user input and flight testing, and ADA for the engine, aircraft integration and flight testing. And we want to go ahead with the Indian academia, I will be coming. Then like all R&D labs, like NAL, CSIR, whatever, CMSIR, all the labs and DPSU, and this we want to take as a national mission. Coming to the manufacturing, once the testing is over, this will be, the Indian industry partner will be becoming the engine production house, where the orders will be placed by the user, whereas both GTRE engine house will be, technology transfer will be happening. The similar way will be going for the product support also, that is for the MRO. So the program will be executed as a national mission. As I said, the technologies are much higher, advanced technologies. For example, 3D blading, non-axiometric end wall contouring, and counter-rotating turbines, advanced blade cooling, damage tolerant methodologies instead of safe life approach, boltless blade retaining arrangement, a list of technologies where the gestation period it will take more. That's why we want to propose for the co-design, co-development. But most of the things we initiated with our COPT, with startups and academia already. And we started with some of the things like powder metallurgy disc, single crystal with EBPVD TBC with our sister laboratory DMRL, large structural castings titanium with PTC Lucknow, like Blix forgings HL, F&F, then PMC bypass duct, CMC nozzle petals with NAL. Already we started. Of course, the TRL levels are less. Once we develop the core, there are a lot of applications, because we are telling there should be a synergy between civil and military, so that can go for a different, variants of the engine. Turbo shaft engine we can go ahead, and civil turbo fan engine we can go ahead, turbo prop engine, and even we can go for the marine. Coming to way forward, conclusions I won't come. Co-design, co-development of advanced high thrust class engine with a know-how, know-why, with a international engine house. Why, I already explained. Basically, we should establish altitude testing. For example, for the last almost 9 months, we are begging Siam to give the time slots. They're not giving because of geopolitical situation. They want to test their engines. Because last 25, some windmill, spool down, auto relay, we have to complete. We are not getting even the time slot. So we should have our altitude test bed, flying test bed, material, manufacturing. As morning Secretary DDR&D mentioned, we don't have our own 50,000 ton hydraulic press, where all the brisks has to be forged. As in India, where it is a national facility. Let it be for NTPC, let it be for BHL, for all of the things. So establishing a material manufacturing testing is a must at this time. Then strategic investment in the aero gas turbine engines. Already everybody brought that thing. For example, only I'm bringing not to any other thing. $250 million we have spent so far on the design development of the Kaveri engine, whereas a flying engine in that class, it requires 2.5 billion. Then pragmatic, long-term, national will is required for the aero engine. Everybody is bringing, yes, we are, for the last 20 years, we are speaking the commission for the aerospace. That is a must actually. Just a minute, I want to bring it out. First we started with 85 kilonewton, then we thought we should go ahead with the 90 kilonewton, That's what Mr. Gavankar is bringing out. I'm little bit more explaining. When that we call as infra, when we have gone ahead, then we thought we should go with the 110. When more going the 110, we thought of now 145. So our will, how to go ahead with all the stakeholders, that's what we are doing now, should be there. Then now, earlier there was not that much synergy, but really we are working with academia, startups, and R&D labs with MSMEs. Then not only, now brought it out, build to spec, not only build to spec, and we have to go even build to concept also. Indian industry today is really agile. For example, single crystal, two major people are there which they could able to do. One high-speed alternator, one firm from Pune, he could able to give for the build to spec. Today, Indian industry is totally different thing. So we should go ahead with that thing. Then, of course, skilled manpower. Now, most of the people are going for the IT. For example, earlier, MTech, PhD should be in the turbo machinery, metallurgy. Nowadays, we are not getting really. Unless otherwise, we have like a rhenium, ruthenium, tungsten. I'm only mentioning. Nobody is going nowadays. So our national, policy to have like a gas turbine special. Earlier, some 4-5 MTech used to be there. Now only one. That is NIT Warangal is there. Turbo machinery. Most of the colleges, they are taken out from their curriculum, which is not good at all actually. So all together, we have to see what is the way forward. Thank you, Jai Hind. Thank you very much.